Hello, my name is Sohel Shaikh, and today I'll be presenting you the numerical simulation of the conjugate convection combined with the thermal conduction. So basically, the convection and the conduction simultaneously using a polynomial interpolation method. So let's go ahead with it. Motivation of the topic. The topic finds its motivation from the fact that the convection and the conduction takes place simultaneously in heat transfer from outside to a building. Now, the thermal physical properties of and the geometric dimensions of the wall. The thermal physical properties means the thermal conductivity, heat transfer coefficient, etc. And the geometric dimensions of the wall, that is the thickness and the length, etc. of the wall, affect the thermal performance of the buildings. Hence, the design of the wall thickness plays an important role in heat transfer between the wall and the surrounding. So the objective of this presentation is we're going to be coupling the convection and the conduction heat transfer. There's not going to be the major thing we're going to be doing in this, except the establishing the relation between the Nusselt number and the thickness of the wall using Lagrange interpolation method will be the major thing we'll be doing. So this is the geometry considered for the modeling. So it has a room in which there is a fluid, and there are adiabatic walls all over it except for one wall. So the heat transfer can take place through this wall. So the same thing is shown in 3D here. So this is the wall through which the heat transfer can take place, and all other are surrounded by adiabatic insulation. So the governing equation for this, basically convection takes place through fluid. So in order to get the solution for the heat transfer through convection, one needs to solve the fluid dynamics equation, that is the Navier-Stokes equation. So these are the equations representing the behavior of the fluid. So this is the conservation of the mass, and this is the momentum equation, basically Newton's equation, force equal to mass into acceleration reduced to a dynamics of the fluid form. And this is the energy equation, which shows the conservation of the energy. Now we won't go into the depth of this solution or finding out the solution, these equations that we see, these solutions, the solution of that is done, the paper that I've studied, the solution is done using SIMPLE, simple algorithm, and they have coupled the momentum as well as the continuity equations in order to solve it. But we won't go into that solution as we're majorly focusing on the data that we get from this. So we'll be using Lagrange polynomial interpolation method to get the polynomial passing through those data points. So this is the data that we get for different wall thicknesses. Nusselt numbers are given using the data from the solution of those equations. So what is Nusselt number? So basically in heat transfer one encounters a lot of dimensionless numbers. So Nusselt number is one of those numbers which represents the convection heat transfer. So if the Nusselt number is high, one can basically say that the convection heat transfer is high. Okay, we'll be getting into more of that in the coming slide. So the data points that we have got, this is the x coordinate and this is the y coordinate. So there are certain points x, y, x, y, x naught, y naught, x1, y1, so on. Now, I'll be explaining first the Lagrange interpolation method for finding the polynomial. So if you have such points x0, y0, x1, y1 up to xn, yn, one can get the polynomial passing through all these data points using the Lagrange interpolation formula. So this formula is y0 l0 plus y1 l1 plus y2 l2 so on up to yn ln. Here y0, y1, y2 are the points, the y coordinates of these points. Now what are L0, L1? So these are the basis polynomials. One can get these basis polynomials using these x coordinates like this. This is the formula. You'll get a better insight of this formula in the next slide. So these are the points we have x0, y0 as 0, 4.5. So these are the points, basically these are the points I'm talking about, 0, 4.5. These are arranged in this form, x0, y0, 0, 4.5, x1, y1 and so on. And this is how we get the basis polynomials for this. So there are four basis polynomials, and L0 equal to x minus x1, x minus x2 into x minus x3. So we don't have x0 here, we just have x minus x1 up to x minus x3 multiplied, and then the x0 that we didn't have here is here, and all other x coordinates are subtracted from it and multiplied accordingly. And these are the this is the substitution of the values in order to get these L0, L1, L2 and L3 basis polynomials. Once we get the basis polynomials, we can easily get the polynomial that is passing through all those data points. So these are the y naught, y1, y2. We easily know those are the numbers. But if you put these basis polynomials, we can get this polynomial that is p of x as a function of x. So the x here represents the thickness of the wall, that is E, and the polynomial p of x is the Nusselt number. So we get the relation between the Nusselt number and the thickness of the wall like this. Now if you plot this, we get the variation of the Nusselt number with the wall thickness. So as the wall thickness increases, the Nusselt number goes on decreasing. Now I might want to tell you about the Rayleigh number here. Rayleigh number is again one of the dimensionless numbers. So this data we get was for Rayleigh number equal to 10 raised to 5. So for various different Rayleigh numbers, we can get different graphs here. Now this you just have to consider this Rayleigh number, different Rayleigh numbers, and the variation of the Nusselt number with respect to that. Don't go into deep of that. So basically our aim is to understand the variation of the Nusselt number with the thickness of the wall. So as you can see, this is the graph for the polynomial we had found out. Okay, so the Nusselt number. I was telling you that if one gets the Nusselt number, one can easily get the heat transfer through convection. How come that? So the Nusselt number is given by h into L by K, where h is the convection heat transfer coefficient, L is the characteristic length, and K is the thermal conductivity of the fluid. So if we get the Nusselt number, we can get the coefficient of heat transfer, convection heat transfer from that. So we can get the heat transfer easily from this, getting this coefficient of heat transfer. So Nusselt number gives us the heat transfer that is taking place through convection. So the conclusion is that by the mathematical modeling of the coupled convection and the conduction, we can get the data points, that is the thickness of the wall versus the Nusselt number. And once we get these data points, certain data points, we can get a polynomial passing through them, and we can simply predict the thickness of the wall for which a particular heat transfer may take place, or for a particular thickness of wall, what may be the heat transfer, we can predict that as well. So then we can basically design the wall thickness and optimize the design of the wall using the Nusselt number and predicting the Nusselt number for a particular wall thickness using this Lagrange interpolation method. Now these are the references. The first one is the research paper from Sage Publications, that is the numerical simulation of the conjugate convection combined with the thermal conduction using polynomial interpolation method. These are the authors. And second one is the numerical method for engineers by Stephen Chapra and Raymond Canal. Thank you.